functions.
Can you see my screen, please? Hello?
Yeah.
Okay, good. Welcome, everybody. Are there any questions before we get started? Okay, I guess this is the last lecture of the semester. And after that, we will have a final take-home exam. And I'm going to give the take-home exam out tomorrow afternoon. And some of you have asked for more time because it is the end of the semester crunch. Some of you feel rather pressured. I can make it due Tuesday rather than Monday. Would that help you if I make it due Tuesday?
Yes.
So that you have one extra day to work on. And for those people who are working out in the industry and working part-time as well as taking this course, you probably do not want this exam to be on the weekdays. So that's why I'm thinking of scheduling it on the weekend. And you can start early. If you start early, you may finish early and you may finish the exam and hand that in early as well, okay? So today I'd like to talk about the quantum coherent state of light. Okay, and this is necessary because some of the things that we have observed are not reasonable. We have studied the quantum pendulum. The reason why we study the quantum pendulum is because we feel that the basic oscillation of an electromagnetic field comes from the oscillation of the electron-positron pair. Okay, when you have electron-positron pair, you can think of them as being a positive charge and a negative charge. And one actually have a mass m, the other one have a negative mass. Okay, together they actually constitute nothingness. But they can lurk in vacuum. And when an electromagnetic field passes through vacuum, the electromagnetic field can polarize these EP pairs. That's why you have B is epsilon naught E plus P. And this is coming from material. Okay, and this is coming from vacuum. And if you have just vacuum alone, then D will be equal to epsilon naught E. And this is something like your polarization current. And this polarization current is coming from the polarization of the electron-positron pair lurking in vacuum. And when the electromagnetic field oscillates, it's because we have a lot of these oscillators, EP pair oscillators. They essentially are in space, okay? And they're coupled to each other through Maxwell's equation. So you can say that Maxwell's equations are equations that couple the EP pairs. You can think of this as minus mu naught dH dt, and then this is like epsilon naught dE dt. Of course, together they form the wave equation. We have derived them before. We show that together, like if you just look at the electric field, it will have something like 1 over c square partial t square E equal to 0. And then we will have the magnetic field being equal to that as well. So that is how electromagnetic waves come about. They are due to the oscillation of the EP pairs. And these EP pairs are harmonic oscillators. You can think of them as very similar to a pendulum. If you think of them as a pendulum hooked to a wall, okay, and they will oscillate, but in addition to being oscillating, they have their classical way of oscillating as well as a quantum wall of oscillation. Okay, the classical way of oscillation is like what we have studied before in the Lorentz Sommerfeld model. So this pendulum can be described by, for instance, an equation something like this. Okay, this you can derive by using Newton's law. And then we show that this equation can also be derived using Hamiltonian mechanics, where the total Hamiltonian of the system is the kinetic energy plus the potential energy. And then with this Hamiltonian viewpoint, we have an alternative way of deriving the equations of motion. And we found that the equations of motion are such that if h is a Hamiltonian is a function of both p and x, then you find that dp dt, okay, which is the velocity or acceleration. This is actually p is mv, which is m dx dt. So this dp dt is actually like m d square x dt square. And then this is given to be the derivative of the Hamiltonian with respect to x, okay? And the Hamiltonian that we had before for a harmonic oscillator is that this p squared over 2m plus half kappa x squared. Okay, and if you differentiate this, you get back the same equations of motion as we had before, which is kappa x. And if you plug this in and differentiate it, you get that to be your Hamiltonian. And then you also get the fact that the x dt is the h dp would be just p over m. Okay, if you take a look at this. And the Hamiltonian mechanics allows us to connect classical mechanics with quantum mechanics, because quantum mechanics is motivated by Hamiltonian mechanics. So in Hamiltonian mechanics, we say that h is a constant, the energy of the system. But then in quantum mechanics, we would like to make h into an operator. Okay, but make h into an operator, and we will have to operate on a wave function. And then it will become like something like E psi xt, but then we say, because E is equal to h bar omega, as motivated by some of the experimental finding, then we say that this should be minus h partial t psi of xt. Okay. So that is how Schrodinger equation comes about. And then Schrodinger equation comes about is because we say that h okay, which in the classical world was h squared k squared over 2m plus half kappa x squared. This is just p squared over 2m. Okay, and this can be replaced by minus partial x h bar partial square partial x square psi xt over 2m. Okay, this becomes, in this is in the classical world, but in the quantum world, you should replace this h bar k square with a differentiation operator, okay, which is should be h square here, sorry. So h square partial x square psi. Okay, psi that would bring down a k square with a minus sign out front. Okay, so that's how Schrodinger equation comes about. It was very much being motivated by Hamiltonian mechanics, but then it changed a completely different way of interpreting the world. That is, you can not think of electron as being having a fixed position and a momentum anymore, but rather an electron now is defined by a wave function. The wave function, in this case, makes the Schrodinger equation look something like plus, and then you can usually write these terms as half m omega naught square x square psi xt, okay, where you have used omega naught square to be, I guess, a kappa over m. Okay, you can write that as kappa over m. And then the right-hand side, you will have something like IH bar partial t psi of xt. Okay, so you have this, which we call the Schrodinger wave equation. You can think of this Schrodinger wave equation is used to describe the pendulum in the quantum world. Originally, we have EP pairs. Okay, EP pairs. And then they are bound together by some forces. And this EP pair will oscillate like a classical pendulum, but they can also oscillate in the quantum world. And to be more appropriate, they should be described by quantum mechanics and hence the Schrodinger wave equation. Okay, so we have this Schrodinger wave equation way of describing the quantum harmonic oscillation. We believe that these quantum harmonic oscillators at the fundamental level, they even exist in vacuum, are responsible for the observed electromagnetic oscillations that we see in the macroscopic level. You can think of space as being having many of these EP pairs resonating in unison collectively, and macroscopically you see the electromagnetic field. Are there any questions regarding this discussion?
Quite stupid question. We have this Schrodinger equation, and in order to solve it, we need to have boundary and initial conditions. So yes. How do they look like?
We will not solve this thing as an initial value problem because there's no driving source in this problem right now. So we can have boundary conditions. The boundary conditions will be that the wave functions are vanishingly small when x goes to infinity. Okay, and that can give you a solution that is unique. But initial condition, we're not worried about it. We won't solve this as an initial value problem. Okay, that's a good question, but we won't solve this as an initial value problem. Instead, we solve this as an eigenvalue problem. And in order to do that, we use the separation of variable and say that the solution has to be something of this form. Okay, something of this form, psi x. Okay. And then if you say that the solution is something of that form, then what we have is that this equation will just become h squared over 2m partial square partial x square. Okay, and then the e to the I omega t will cancel out through the equation. Then you have just phi x over here. And then you would have the second term as being half m omega naught square x square psi of x. Okay, I'm just canceling out the e to the minus omega t term everywhere. This should be a minus, sorry. Because we are talking about physics. And we always use e to the minus I omega t time dependence. And then if you put that in, then you will have, this will become minus I omega together with give you h bar omega. H bar omega, let's just call that e psi x. Okay, here will be just h bar omega. And if you look at this problem now, it is an eigenvalue problem because it is of the form of a linear operator operating on a function x is equal to a constant times a function x. And you can always think of a function of x as a vector. So this can be thought of as a matrix times a vector v equal to an eigenvalue times a vector v. Okay, so now we are casting the Schrodinger equation problem into an eigenvalue problem. And it turns out that this equation has infinitely many eigenmodes. And I show you those eigenmodes in the last lecture. Okay, and let's talk about more ways to solve this Schrodinger equation. One way to solve this Schrodinger equation to make it more compact is to write it using dimensionless unit. So if I write this using dimensionless unit, what I should have then is that I like to divide the whole equation, okay, the whole equation by h bar omega naught to make it dimensionless, because this has an energy of E, and if I divide by that, I get h bar omega naught been having the same unit, then the equation will become dimensionless. And it turns out that if you choose a change of variable for the length, c, you let c be equal to m omega naught over h bar x, okay, replace the space variable by this c variable, and then you can actually change this equation into a dimensionless equation that would look something like this, like half. I won't go through the change of variable for you. I think I did that the last time in the last lecture. Okay, and then psi of c is equal to E over h bar omega naught psi of c. Okay, well, all these are dimensionless variables now. Psi is dimensionless. Okay, and I can write this eigenvalue problem in more compact fashion if I factorize this. It turns out that this term looks like minus a squared plus b squared kind of thing. Perhaps I can write it as minus a plus b times a plus b, okay? But it's not that simple because these are differential operators. For algebraic values, scalar variables, this is quite straightforward. But then for differential operator, the factorization is more complicated because if you multiply two of these operators together, like if I take this operator, which look like the square root of one of this operator, okay, and then multiply by another factor, it does not exactly factorize the above equation because if you multiply it out, you should have 4 terms. You should have 4 terms, and then you find that the 4 terms are, I won't go through the details. Everybody knows how to multiply these 4 terms out. You get half d squared d zeta squared plus, that's not zeta, cos c squared Okay, I only have two terms, but then there are some cross terms that you should be careful about. And those cross terms give you dd cos c minus cos c dd cos c. Okay, for scalar variables, if these are scalar variables, these two would have canceled each other right away. And you will have only two terms, just like the scalar variables there. But these are not scalar variables, these are operators, differential operators. Then you have these two terms left. And it turns out they can show that these two terms do not actually precisely cancel each other, but they're equivalent to an identity operator in this sense that if you have this thing, if you multiply this, and if you multiply this to a function of cos c, you can show that it always gives function of cos c back. Okay. Okay, which means that this differential operator is an identity operator. You can show this quite easily. Okay, let me show it just in case you are interested. Okay, so if you take dd cos c minus cos c dd cos c of any function of cos c, okay, the first term is using the chain rule. It will give you f of cos c, f of cos c if you use the chain rule, plus cos c dd cos c f cos c, right? The second term is minus cos c dd cos c f of cos c, and again this is equal to, there's no chain rule to apply here, minus cos c dd cos c of f cos c. So the second term just cancel this term. Okay, so if you add the two terms together, this is just f of cos c. So this is an identity operator. It means that no matter what functions it operates on, it always gives that function back. Okay, so this factorization is simplified because this is just an identity operator. You can then say that the thing that we want to factorize would be equal to a partial factorization, which is partially successful using the old way of thinking, and then 1 over root 2 d cos c plus cos c plus a term that accounts for this last term. Okay, the last term, it turns out to be equivalent to an identity operator, and so you should put half at the end to account for the last term. And then what you have is that this Schrodinger equation that we have had, you convert this Schrodinger equation in normalized unit into one that looks like this, okay? And then we factorize it to look like this, okay? And what you have is that Schrodinger equation can be written as these two operators plus half times that function. So if this is operating on any function, okay, if this is operating on any function of cos c, yes, any questions so far? Let me just write this as a function cos c. Then it can be written as this term, okay? This term, we can call it a dagger operator or the annihilation operator. Okay, so it should be a dagger. And then this term, we call it the raising operator or the creation operator. Okay, and we just call it that. And then plus half f of cos t. So Schrodinger equation can be written in dimensionless unit using two operators. Those two operators are frequently used. They are called the annihilation operator. Annihilation operator. And this is called the creation operator. And this is also called the lowering operator. Sorry, this is called the creation operator. It should be opposite. This should be called the annihilation operator. And this is the creation operator. Annihilation sometimes is also called the lowering operator. And then the creation operator is sometimes called the raising operator. Okay, these are the alternative names that you might find in the literature. And they have this very interesting property that is used a lot in quantum theory, which I would not derive, but you can easily derive it by plugging, doing back substitution. That is that if you take the commutator of two operators, the definition of this notation is that this thing, by mathematical definition, is this operator operating on this minus this. For most scalar number, this is equal to each other. So if I have two scalar numbers, A and B, okay, if these are scalars, then this will be AB minus BA, and always equal to 0 if they're scalar. But if they're matrix operator, examples of operators where this would not go to 0 are matrix operator or infinite dimensional operators. You can think of the operators that we have in our course as being infinite dimensional matrix operator or Hilbert space operator, and they do not commute. Okay, you cannot change their order. If you can change the order of A and A dagger, then this would have been 0. But in general, this is not 0. And in general, this is actually equal to the identity operator, which is not equal to 0. Hence, these two operators can be easily shown to not commuting with each other. Okay, they do not commute with each other. And because of this property, I can write Schrodinger equation, which I have factorized. I have written the Schrodinger equation, which I have factorized. Okay, if I go back to this Schrodinger equation, which I have factorized in this manner, okay, what I have shown is that this factor can be written as half let me see, can be written as actually A dagger plus half. Okay, that's what this factorization is showing over here. If I look at this factorization and look at the definition, I have been able to factorize the thing. Sorry, this should be A dagger A. Okay, and if you go back and trace the algebra, that is essentially what I have done. Okay, this Schrodinger equation in dimensionless unit can be written as this. And if you want to be consistent, you might put the identity operator here as well. Because the two terms are operators, you might as well call the second term identity operator as well. And you can convert Schrodinger equation into a form that is something quite simple. So which is A dagger A plus half operating on a wave function is equal to E over H bar omega naught psi of the C. Okay, that is your Schrodinger equation in normalized units. Any questions so far?
Yes, I have a question, Professor Chu.
Sure.
You call this raising sign on the raising operator, you call this dagger. Is it plus or dagger? It's a little bit confusing.
Dagger here means Hermitian conjugate. Okay, in matrix algebra, when we have a symbol like this, is called a dagger. It implies Hermitian conjugate or conjugate transpose. Okay, you might have come across this notation in your linear algebra class. A dagger of a matrix A means you take the Hermitian conjugate or the conjugate transpose of the matrix A. The same thing applies here. The dagger on a Hilbert space operator A means that you take the Hermitian conjugate or the conjugate transpose, not the plus sign. It's a dagger sign. Okay, is that clear?
So you denote the creation operator by dagger sign, right?
Yeah, I think so. Yeah, the creation operator is having a dagger sign. Okay, and because of this identity, you can also very easily use this identity and rewrite this equation into a form that is half A dagger A plus A dagger psi is equal to E over H bar omega naught psi. Okay, just using this identity operator, you can replace the A dagger with 1 minus this one. Okay, you can actually break this into half, and then you can convert half of them into the other one, and then you have a form that's more symmetric to look at if you want to. Okay, because if you look at this form, it's quite clearly that it's more symmetric compared to this form. Okay, so this equation has been solved over and over again because it actually is a first order ODE, and it has been solved over and over again, and it has been solved as an eigenvalue problem by many people because this equation is just Schrodinger equation for the harmonic oscillator. Okay, and if I write this in direct notation, it will look something like this. In direct notation, you denote a vector by a cat. Okay, this is called a cat. In direct notation, a cat is nothing but a vector. Direct way of denoting a vector. Okay, cat vector. Okay, and it turns out that this equation has closed form. The closed form solutions can be found using Hermite Gaussian polynomials. So I will not discuss the closed form solutions. And the eigenvalues also can be found. You can show that En, if you think of this as the eigenvalue problem, the eigenvalues is just equal to n plus half. Okay, so they have closed form eigenvalues. And furthermore, because of this, that this being equal to that, you can easily see by plugging this back into the equation that A dagger A operating on this function is equal to n psi sub n. Okay, psi sub n is an eigenfunction. And of course, there are many different names for it. Eigenfunction, eigenvector. Okay, it's an eigenfunction or eigenvector because it is very analogous to a matrix eigenvalue problem. We have an operator operating on the vector is equal to an eigenvalue times the vector. Okay, so this is an eigenvector of this equation, and since it has an eigenvalue of n, it actually is proportional to the photon energy, because if you count n times h bar omega naught, it is actually the energy of a photon. And this eigenvector is also called the photon number state in the language of quantum optics, photon number state, or Fock state. Okay. Okay. And this operator is called a number operator. Because when it operates on the photon number state, it gives you the number of photons that are associated with that state. Any questions so far? And the reason why they are called raising and lowering operator or annihilation and creation operator is because if you were to take the closed form solution of this, which is expressible in terms of Hermite Gaussian functions, I'm not going to write those functions down. You can look up in many books. The closed form solution to this equation is in terms of Hermite Gaussian functions. Okay, so if you look at this function x, it can be written as in terms of Hermite Gaussian function. And then if I were to use direct notation to write this thing, okay, in direct notation, it says that a lowering operator operating on the Fock state or photon number state will give you n times a new Fock state or photon number state with one less photon number. That's why this is called a lowering operator. It essentially makes the eigenstate descend from a high eigenvalue state to a lower eigenvalue state. And oftentimes, you also find that if you have the creation operator, okay, the first one is called the lowering operator or the annihilation operator. The second one is called the raising operator, okay, or the creation operator. And this one, you can go through the algebra by direct substitution, because these are known in closed form. You know what the A, dagger, and A are. You can plug and chuck and find that this is true. So the raising operator, okay, or the creation operator, actually would raise the state of the photon number state by 1, increasing the number of photons that it has. But usually this is written in a rather cryptic notation in the physics literature. They will just write it like this. So the photon number state is just denoted by the cat n, okay? And then that equation will be written in this manner. And then in a more cryptic notation, this raising operator operating on the photon number state is just equal to n plus 1 times n plus 1. Okay. So any questions so far? I'm not going to go into the detail of this eigenfunctions or eigenvectors. They're given in textbooks. You can find them in almost all quantum mechanics books. Okay, so there's always a eigenvalue, eigenfunction, something associated with an operator and so on. But I like to point out to the fact that in quantum theory, everything is random. So if you have a momentum, okay, in quantum theory, it becomes a random variable. And it becomes momentum becomes a random variable. Because it's a random variable, it cannot be described by just one number. It has to be described by an operator and a vector. Okay, so in associate with this operator, you have to define a state vector. And similarly, if you have a position variable, which in classical theory is a deterministic scalar variable, in the quantum world, it will have to be replaced by a operator in this manner, together with a state vector. And the mean of the operator is given by this value. Okay, this is a cat and a bra, okay, a bra and a cat. And this is called the average value. Because P is a random variable now, it has an average value, and that average value is denoted by P bar, okay, the random variable that is associated with P hat. And similarly, you can show that this is also a random variable with a mean value, which I call S bar, okay? Which means that if you write this in more explicit notation, it says that, P in the quantum world can be, for instance, replaced by I H bar partial X, okay, becomes an operator that looks like that. And psi, if I write it more explicitly, might be something like this. And then X hat in very simple notation is just X. And then if I were to find this expectation value, like this one over here, okay, what you do is to find inner product. This inner product can be written as psi of X, X, psi of X. And there should, since this is a conjugate transpose, there should be a conjugation over there, okay, and that gives you the average value of X. So this together gives you the expectation value, because you can also write this as, you can bring these two together, okay, and write this as a expectation value in this manner. This is called the expectation value of X hat. And this has the property of a probability density function. So the wave function square, okay, actually gives you the probability density function. And you have to integrate this random variable multiplied by this probability density function, integrate over Rx, and that will give you the average value of the random variable. Okay. Something becomes a random variable, it has to be described by more things. It has to be described by a wave function rather than just one single variable. Okay, and this random variable has a mean and also a standard deviation. Okay. So, are there any questions so far? So, what I'd like to talk about next is then the coherent state, because the photon number states are rather bizarre. They are, in a sense that they have always zero mean. If you look at the photon number state, they look something like this, or they might look something like this. And if you were to look for the value of the position described by this thing, it always equal to 0. So it is non-classical, because this states of the quantum pendulum solved from Schrodinger equation always gives you a state whose expectation value of the position of the electron or the displacement of this electron-positron pair, okay? That displacement is always 0, and we call this non-classical. These states do not have classical equivalent, but if you know that, well, if you have a pendulum, classically we know that the motion of this pendulum is going to, if I were to plot x as a function of t, is going to oscillate like this, okay? And I'm not seeing any of this thing coming out of this photon number state or the Fock state or something. So something must be very wrong. Okay, not wrong in the sense that the mathematics is wrong, but the interpretation is not correct. So it took a while for physicists to find out the remedy to this problem, you actually have to find a state called a coherent state, where you can actually see you would have to find the coherent state. This coherent state is actually a superposition of, let's denote this state by alpha, okay? It is actually a linear superposition of the photon number state. Okay, and another way of saying what the coherent state is that it is a eigenfunction of the annihilation operator, that if you let the annihilation operator or the lowering operator operating on this coherent state, it should return a number. This number is usually complex, okay, times the coherent state. And this notation might be confusing, but you might want to think about this as is equal to alpha, f alpha of Cauchy. Then, since these are all differential operators with the Cauchy variable, I can also write it more explicitly like that. But physicists usually just like to write it, I guess, very tersely and very cryptically, in a very cryptic way, just as this. And this is the same as this. If you can't understand this, try to down translate it back to this. Then you see a function, you see a differential operator, you see an eigenvalue. Okay, this eigenvalue is complex. And do you know why this eigenvalue is complex? Why this eigenvalue has to be complex? When would a matrix operator have real eigenvalues? When the matrix operator is Hermitian. Okay, when the matrix operator is Hermitian. It turns out that in this case, the matrix operator A hat is a non-Hermitian operator because it's defined. It's harder to prove it, but maybe it can be seen one way or another, which is because we define the A operator to be this function over here. Okay, you can show that the conjugate transpose of this operator is actually this. Mathematically, you can show that the conjugate transpose of this operator is this operator. Okay, and to define what the conjugate transpose is kind of tricky in a Hilbert space. In the Hilbert space, you actually have to define it using inner products. And I sort of discussed about this in one of the lecture notes. So if you use inner product, you can actually show that these two operators, this is the Hermitian conjugate of this, and you take the Hermitian conjugate of this, you get this. Okay, so you can think of the coherent state, which is a linear superposition of the photon number states, which are the eigenstate of this equation over here that we have over here. Okay, and if you choose the C sub n judiciously, this alpha can become an eigenvector of the annihilation or the lowering operator. And how do we do that? Well, we do that by its definition. We define this coherent state to be this. So if I were to operate the coherent state by this thing, and if I substitute this definition of the coherent state into this equation, then this should be equal to 0 to infinity Cn A hat n. Okay, and by definition of what the lowering operator is, it will take a photon number state and lower it, and that we had defined before. Okay, the lowering operator will just lower the photon number state by 1. Okay, so if you take that to be the definition, then this second equality would just become well, what I mean here is that it will lower things by 1, but then the n equal to 0 state, you cannot lower anymore. It will just make it 0. You can show that if this is the n equal to 0 state, the lowering operator operating on it should become 0. This you can demonstrate by explicit substitution, because these functions are all given in the textbook. These are just Hermite Gaussian polynomials. Okay, these are just Hermite Gaussian polynomials. And if you plug the Hermite Gaussian polynomial definition of this photon number state into this equation, you can show that when you have the lowering operator, when n is equal to 0, it just makes it 0. So you can drop one of the terms, the beginning terms. Okay. And then you use the fact that this always lowers this photon number state by 1. And then you will have this being equal to n is equal to 1 to infinity Cn, using the property that we have defined for the lowering operator over here, which I did not prove, but you can actually convince yourself by back substitution. Okay. You use this property. This is the lowering operator. And then they can write this second sum as square root of n minus 1, using Dirac's notation. Sorry, there's no bar over n, just n. Okay. So are you with me so far? So I'm just writing this as a linear superposition of photon number states, requiring this linear superposition to be an eigenstate or eigenvalue of this operator, and then it has to satisfy this relationship. And now I don't like this n minus 1 over here. I'm going to change variable and call n prime equal to n minus 1. Okay, I can just do a dummy change of variable that we usually do in mathematics. If you have a summation, you can change the range of summations, the index of the summation, by just doing a dummy change of variable. Okay, in this manner. And then if I sum over n prime, it will go from 0 to infinity instead of 1 to infinity. And then the summation indices would change inside this summation. So let me call it n again, just not to be confusing. Okay, it just becomes that. Are you with me? Okay, but by definition, that this should be the coherent state, or the eigenfunction of the lowering operator, or the lowering operator, or the annihilation operator. Then this should be proportional to the coherent state, should be equal to this again times the necessary constant out front. Okay, using this equation. The left-hand side, I just back substitute this and do some algebra, and it should be equal to the right-hand side. And now if I look at what the right-hand side is now, okay, I would have this being equal to, again, using my definition of alpha, this would be just equal to alpha, n equal to 0 to infinity CNN. Okay, but these two series are supposed to be equal to each other, this series and this series. Okay, these series are supposed to be equal to each other. But then you know that the photon number states are eigenstates. Eigenstates are orthogonal to each other. In fact, you have chosen the eigenstates here to be orthonormal, in the sense that if you take n prime and n, it will be equal to 0 unless n and n prime are equal to each other. This is called orthonormality. And because of orthonormality, the coefficients of these two series must be equal to each other. Okay, the coefficients of these two series must be equal to each other. Like if you were to equate two Fourier series, since the Fourier series terms are all orthogonal or normal, the coefficients of those Fourier series are equal to each other. Okay, so you come up with a new equation that Cn plus 1 must be alpha Cn divided by square root of n plus 1, right? If you look at this equation, if you equate these two coefficients, you get this equation. And this equation allows you to recursively solve for the value of Cn plus 1 in terms of Cn, Cn in terms of Cn minus 1, and so on. So if you recursively apply this equation, you have Cn be equal to Cn minus 1 alpha over square root of n, and then Cn minus 2 alpha square square root of n minus 1, and then equal to dot 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 equal to C0 alpha n over square root of n factorial. Okay, you find this to be true. So all the Cn's that you have in the summation can be expressed in terms of the first C0 of the summation, and then the rest you can just put inside. When what you have then is that the coherent state, which we started out by deriving in this manner, but we find an equation for C sub n, and then this should be equal to C sub 0, n is equal to 0 to infinity alpha n over square root of n factorial n. Okay, so that is the coherent state. Okay, voila, you have the coherent state. But this is a quantum state. Quantum states have the property that they have to have normalization of 1 because they have this probabilistic interpretation. In other words, a quantum state, if I write this in an explicit notation, okay, this inner product will be something like this. And since this inner product is something like this, and this type of function, the interpretation, the probability density function, this has to integrate to 1. Okay, so if you use this normalization condition, you can actually figure out what C naught square should be, and you can find that C naught is e to the minus alpha square over 2. And then you can figure out what the coherent state is. Okay, so are there any questions on the derivation of the coherent state?
So I have a question.
Okay,
I have
sure.
a question on physical meaning of this coherent state.
Okay. The physical meaning of this coherent state is that it is a linear superposition of the photon number states. The photon number states are not physical in the sense that they're all spread out. And it turns out that if you plot this coherent state now, it looks like a wave packet. Instead of it looking like this, it's spread out, coherent state will have something localized. It is localized. This is a function of Cassis, a coherent state have this localization behavior. We demonstrate that in a little while, why it is localized.
So can we think of it as a wave packet?
Yeah, you can think of it as a wave packet. Yeah, that's a good point. You add a lot of these photon number states, each of them looking like this, okay? But if you add them judiciously together, you can form a wave packet. The wave packet describes the time evolution of a pendulum more properly, okay? So the interesting thing would be to see how this thing evolves in time, how this coherent state evolves with time, okay? So we like to study is time evolution. And to study its time evolution, we have to solve a Schrodinger equation which is this equation here. If I write it in direct notation, it would be something like this. Okay. And then if you solve this equation, it can be solved formally. It can be solved formally since this is a constant. Okay, I can write my psi as being equal to e to the minus IH hat t over h bar psi. Okay, this is the formal solution to the above. The only trick here is that might baffle you is that what does it mean? This is an operator. In Schrodinger equation, remember h hat is p hat squared over 2m plus half m omega naught squared x hat squared. So this is an operator. What does it mean to have an operator in the exponent? You remember p hat is an operator, is IH bar partial x. So what does it mean to have an operator in the exponent of a function? Does anybody know, or you want me to explain what that means?
This looks like just the same as matrix exponent.
Yeah, it's
Like,
very similar to matrix exponent. Would you know how to take the exponent of a matrix? Do you have enough linear algebra background to take the exponential of a matrix? Okay, if not, then I'd like to discuss that briefly. So it can be generalized to a more general problem. What does it mean to take a function of a matrix operator? Okay, functions of a matrix operator. You can think of this as being having a Taylor series expansion, that if you have a function of x, can be anything, can be a function of c, for instance, then it can be written as a Taylor series expansion plus f prime of c with c linear term, and then you can have f double prime, sorry, this should be 0, Taylor series expansion over 2 factorial c squared, okay, plus f triple thing 3 factorial 0, and then c cube. You're familiar with this Taylor series expansion. You can use the definition of a Taylor series expansion to define what the function of an operator is. So if I were to use this Taylor series expansion, then f of a would be equal to I times f of 0. And then the second term, I just replace c with the operator. Okay. And then the third term, I would just have with the operator squared plus the other terms. Okay. But then what is the meaning of the series that consisting of operators and the power of the operator? In order to get meaning out of this, you need to operate this. You need to operate this on the vector. Okay, say if you have a vector which is the eigenvector of A, you find an eigenvector of A that has this meaning. Then you can make meaning or add meaning to this series by letting it, sorry, it shouldn't be like this. You can add meaning to this operator by letting the whole series that you have on the left or on the right operating on the vector V. And if I do that, the first term will just become f of 0v. Okay, because I have an identity operator on the first term. The second term will just become f prime of 0, a dot v. Okay, the third term will just become f double prime of 0 over 2 factorial a squared dot b. Okay, and then it will go on, and then some of the terms will an dot b kind of thing. Okay, it becomes something that looks like that. But the evaluation of a power of an operator on a vector is very simple. We just apply this equation a few times. Here you apply it 2 times, here you apply it one time, here you apply it n times. And so this series just become F0 V plus F prime 0 lambda V plus F double prime 0 over 2 factorial lambda square V plus and so on. Okay. And you notice that this is just a Taylor series expansion again. Okay, if I put V outside, this just becomes F of lambda dot V. So you can resum the series and think of the series as being having the operator in the function be evaluated with the eigenvalue times the eigenvector V. Okay, so if you have a exponential of an operator operating on the vector V, and if V is the eigenvector of A, this just becomes lambda V. Okay, using this rule. This operate on V becomes that, that operate on that becomes that. Okay. Similarly, if you have an infinite dimensional matrix operator, which is what you find here, operating on this, and if you can expand this in terms of the eigenvectors of each hat, then you can actually simplify this thing quite easily using this power series expansion ideal. So let's do that, and then let's find the eigenvectors or the eigenfunctions of the H hat operator. Remember, H hat operator operating on a photon number state gives me H bar omega n photon number state. And that omega n is just H bar omega naught n plus half. Those has already been found in closed form. Okay, so we know all these eigenvectors, which are the photon number states. And we also know the eigenvalues. And so if you apply this rule to this function, n, okay, if this operates on the eigenvector n, then this would just become minus I omega nt times the eigenvector n, okay? Because we know of this property. We know the eigenfunctions, the eigenvectors. So if we want to study the time evolution of the coherent state using this equation over here, we want to find the time evolution of the coherent state using this equation over here, which is a solution to this Schrodinger equation, then we can say that the coherent state at a certain time t, okay, would be just equal to this time evolution operator operating on the coherent state at the beginning in time, okay? And let's assume that the coherent state is of this form in the beginning in time. We have already found it, okay? We found a coherent state. We found the coherent state to be here. Okay, we found the coherent state and we found the C naught to be something like this, okay? And we can plug this back in here and let the coherent state operate, be substituted with the photon number state. And then what you have then is that you will have this minus alpha square over 2. The photon number states pops up now. Okay. And then you will have this alpha n e to the minus omega nt over n factorial times the photon number state. What I have done here is to let this operator operating on each term of this summation that I have here. Okay, I have found the coherent state to be this one. Okay, and I now operate it with this time evolution operator. I take this operator inside this summation and let it operate on each of these photon number states. And when this operator operates on the photon number states, it just gives you this scalar value back, okay, by the rule of the exponentiation of the function of an operator. So I get this rather complicated looking things. But you can actually resum this and write this together and say that this can be written as just one notation, because omega n, you notice, is omega naught n plus half. Okay, from this equation, omega n is omega naught plus n plus half. And then if you plug that in, you can show that the n can be summed with this term and then leave the other half term outside. And so finally, what you have is that this half omega naught term comes out. Okay, you still have this factor out there. And then the omega naught n can be lumped together and put all to the power of n. Okay, this omega naught n can be lumped together with that, and then the whole thing be written like that. Okay, so what you have is that, well, this looks strikingly familiar because this just looks like a coherent state with a different eigenvalue now. If I compare this thing with the coherent state that I have found previously, which is this one, okay, where C naught is here, and I found that this looks strikingly like a coherent state, except that the alpha that I have now has to be replaced by this alpha naught. This should be a T here, sorry. It should be a T. Okay, it should be replaced by that. Okay, that should be replaced by that. Then you can show that you can show that the coherent state will time evolve in such a manner that it is essentially looks like a coherent state, but with different eigenvalues. Okay, it looks essentially like a coherent state, but with different eigenvalues. Before that, the eigenvalue was just what we had before. Let me see. I can show it to you. Was the eigenvalue was alpha, but the eigenvalue now just becomes something multiplied by an exponential function. Okay, so the derivation is rather long. Okay, I don't have time to show the details, but what ultimately come up to is that so if you were to think of the annihilation operator, or this is the raising operator, has been this thing, and then you have the lowering operator, annihilation, and the creation operator. Okay, this is a lowering operator being equal to this. Okay, and then you can define a new variable and calling this to be 1 over square root of 2 I pi hat plus c hat, and then essentially call this c hat, but this kind of a normalized momentum. Okay, this, remember this momentum in position kind of thing. Okay, and then you can write this as minus I pi hat plus c hat. Okay, and then you can easily show that the position operator is given to be this. Okay, which is just ci, actually, it just comes out to be this. Actually, it does not have any operator with. If you add these two operators, only this term remains. So it's just ci. And then you can show that pi hat is equal to I over root 2 a dagger minus a dagger, and it just becomes minus I d because c. Okay, so what is the point of this? The point of this is that A and A dagger are non-Hermitian operators. Because they're not Hermitian operator, they cannot represent anything that becomes real value if you take the expectation values of them. So we have to find operators where when you take the expectation value of them, they become real value. And this is something related to the position of the particle. This is something that related to the momentum of the particle. And you notice that these two operators are Hermitian, because if you take the Hermitian conjugate of this term, it is itself. If you take the Hermitian conjugate of this plus this, it is itself. So these two operators are Hermitian. And it turns out that they have to be Hermitian since they represent position and momentum. Position has to be something that becomes real if measured in the lab. And momentum also has to become something real if you were to measure in the lab. So if we take the expectation value of these two operators with respect to the coherent state, okay, say if I just take this one, okay, which is like taking the average of this thing, and if you were to go through the math and do this, you'll find that this is just like plugging this back in there. Okay, and then it is quite easy to show that this thing is equivalent to the conjugate transpose. Okay, conjugate transpose of the thing, and you can show that this actually is equal to the eigenvalue Hermitian conjugate, because this notation in Dirac's notation is very similar to the fact that if I have a matrix A times X, if I take its conjugate transpose, okay, is equal to X conjugate transpose times A Hermitian conjugate. Okay, this is just matrix algebra. And if you use that kind of notation, and this alpha is an eigenvector of the annihilation operator or the lowering operator. But if you write this in terms of the other notation, if you think of this as being A alpha if you take the conjugate transpose of this matrix times the vector operation, okay, think of this as a matrix vector product dot, and you take its conjugate transpose like here, you will get above expression. But alpha is in fact an eigenfunction of A hat, the annihilation operator. So you will get an alpha out, but if you take the conjugate transpose, this alpha becomes a bra instead of a cat, and then this A eigenvalues becomes alpha dagger. Okay, so you can simplify this by using that, and then what happens then is that you will have this being equal to the expectation value of the position, okay, which is alpha cos C hat alpha, would be equal to everything can be replaced by eigenvalues now. Okay, the first term, as I said before, can be replaced by eigenvalue conjugate. So I can actually now replace the first term with eigenvalue conjugate. The second term is easy to see. This alpha is a eigenvector of the annihilation operator. This just becomes alpha. And then what I have left with is actually alpha, alpha. Okay, alpha, alpha, because these are eigenvectors of this thing, and then you can write it in this manner. And alpha, alpha is just one. Okay, because they're normalized eigenvectors. And then this just will become square root of, this will become the 2 times the real part. So it will be actually 2 times the real part of alpha. Okay, and alpha is in general a complex number. Okay, and you can repeat this process when alpha becomes a complex number, like becomes like alpha e to the minus I omega naught t. Okay, becomes a time-dependent eigenfunction or eigenvalue. Okay, as you can see, if you were to time evolve the coherent state, each of the term would time evolve in such a manner effectively the time evolves coherently so that only the eigenvalue changes with time in this manner. So the eigenvalues becomes something like this. And if you go through the same process as we did before, you can show that the C will become time dependent. And then you will have this time dependent thing. And then you can show that this actually, after going through the algebra, is just equal to this. Which means that the position becomes time harmonic. The expectation value of the position averaged by this coherent state becomes time harmonic, becomes a sinusoidal signal. By the same token, you can show that the momentum, okay, if you were to take its expectation value with respect to the coherent state, would be something like this. Okay, so what you don't see in the photon number state, you can see in the coherent state, which is that these are some of the things I showed before, and that you can see that the coherent state will correspond to a wave packet. And the wave packet has the mean. The mean was given by what we have found. Okay, we have found it to be having this average value of sinusoidal function in time. And then the momentum is also behaving sinusoidal in time. And if you were to track the average value of the position of the pendulum now, it actually goes back and forth just like a pendulum. Okay. And there are many other fancy things you can do. That you can play with squeeze light. The only difference here from a classical pendulum is that this pendulum does not have a sharply defined position. It has a spread in its position value. Okay, uncertainty is position value. You can describe this uncertainty by maybe a small sphere. Okay, and let it rotate around in the phase plane and make up a sinusoidal function that has uncertainty in its amplitude. You can play around with squeezed light or squeezed state so that you can actually reduce the uncertainty at certain location in time, okay, and so on. So that's, I guess I better stop here. I hope you get something useful out of this. That is that the coherent state essentially let you connect back to the time oscillation of a classical pendulum, but only in the average sense, because the coherent state gives you the oscillation of the pendulum, but with the randomness in its amplitude. But the mean value of the pendulum position resembles that of a classical pendulum. Okay, I'll stop here unless you have any questions. Do you have any questions? Okay, I will write this out more carefully in the lecture notes. And I will write down this even more in the lecture notes, but I would not hold you responsible for it in the exam. Whatever I talked about in the lecture, I might ask a very simple question in the exam, but whatever I write out more in the lecture notes, I don't hold you responsible for the exam. Okay? Is that fair?
Yeah, that's fair. I have a question.
Okay, sure.
So how difficult is it to remain that state coherent?
Well, actually, they're quite stable. They have found to be quite stable, and they can be even measured in the lab. If they're unstable, then we'll be in a very bizarre world, because we want to see that when you put more and more photons together, you will put more and more photon number states together. Okay, if you put more and more photons, you want to see classical optics emerging. And if this summation, if this linear superposition is unstable, you would never be able to see classical optics coming out. And because of the stability, you can show that the more photons you add the more photon number states you add to this linear superposition, the sharper the wave packet would be, and the more it resembles a classical oscillation. So it's very stable, I would say.
Okay, that makes sense.
Otherwise, you cannot see classical physics coming out of quantum physics.
Yeah, I was wondering because if thinking about it as a wave packet, those waves are interfering constructively, which probably needs to be maintained somehow.
Yeah, they have to add judiciously in phase so that the eigenvalue remains the same except for a time change in the phase. Okay, but this is just the magic of the mathematics, and of course the important thing is that you have to see this in the laboratory as well. And if you don't have this physics in the laboratory, then you don't have classical optics coming out. What this theory is telling us is that the more photons we add to this series, which is this series that we have up here, the more photons we add to this series, the more it looks like a classical wave packet. Okay. And it's a stable process.
And the last question, does plane wave exist in quantum mechanics?
Plane wave actually is something that is artifact of our imagination on paper. You study course, in the beginning we had plane wave. We studied plane wave because it's very simple. Okay. But the closest thing that we can have to a plane wave in the real world is a spherical wave. A spherical wave is easy to generate. You can have a point source. Any finite source would generate a spherical wave. You can see that from mathematics. And this spherical waves resemble a plane wave when you are very, very far away from the source point. Okay, can you see that? So you can think of a plane wave as an approximation of a spherical wave.
So yeah, I remember that the Breuil wave, it has some issues with normalization of quantum mechanics. That's why I'm asking.
Yeah, I don't know what you mean by that, because if you were to do quantum theory using just plane wave alone, plane wave by definition is something that has uniform energy throughout all of space. Okay, so it will have infinite energy, and that is not physical.
Yeah, and that's why it's not normalizable in quantum mechanics.
It's not normalizable, but if you think of the real world you have in the world are actually spherical waves. So you don't have this irony of not being able to normalize the plane wave. Okay.
Yeah, that makes sense.
Okay. I'll let you go then. And tonight, Bo-Yun will hold an office hour. You can ask him more questions. You have not asked enough last night. Okay, I'll let you go then.
Thank you.
Okay, bye-bye.
Thank you, Professor